Evening and welcome to another edition of Kung Fu Physics, where we are working our way through Practice Physics GRE problems. The one that I want to do tonight is number 3 off of the 2001 exam. Right there, number 3, 2001. It's a pretty simple sort of mechanics problem. I would also say it's kind of in the realm of an astrophysics problem. I mean, really, it's hard to say where those two fields cross into each other. When you're talking about the physics of something in an orbit, you could easily consider that just a mechanics problem because you study orbits in freshman physics, but it's kind of also an astrophysics, advanced topics, whatever problem. But this problem's pretty easy itself. As usual, I glance at the answers quickly. They don't help me that much because it's kind of a little word puzzle game. So I need to read the text to get anything much. I mean, they're different, but basically I realize right off the bat looking at those answers that I'm going to be analyzing those answers a lot more in depth after I read the problem itself. So let's do it. Number 3, a satellite of mass little m orbits a planet of mass big M in a circular orbit of radius big R. The time required for one revolution is, and then I have all of those options. So basically, I need to go through these answers one at a time. I need to take that time. I'm not going to be able to just pick one of the answers and find it. I need to go through them. So answer A, the time required for one revolution is independent of big M. Intuitively, that just seems very wrong to me because I know that the mass of the planet determines how much gravitational force is present there. And so certainly the way that an object is going to orbit is going to be dependent on what it's orbiting, the mass. So just intuitively, that one gets tossed out pretty quick. Is it proportional to the square root of little m? No, and I guess I wouldn't think too much about that myself, but I want you to consider there's actually another physics GRE problem that has something like this on there. Stuff that when you look at the period of something that's in orbit, it's independent of that something's mass, as long as that mass is fairly small. So, the mass would have to be really big to have its own gravity and be pulling back on the Earth and doing all that. Then it would affect something. But as is a small satellite is not going to do that. It's kind of a cheap answer actually because they say it's a satellite, but they don't specify that it's a small satellite. I mean, if this is a satellite that's one half if little m is one half of big M, then that's going to screw stuff up. They probably saved themselves by wording the problem by saying it's a circular orbit. Because whenever you get a circular orbit, you know that whatever's at the center is going to be vastly more massive than the stuff that the little object that's orbiting a circular orbit. So I'm going on and on. One other thing to think about, if you don't know why, a reason you can immediately eliminate why the period of a satellite is not dependent on the mass of a satellite. I want you to think about the space station. Okay? You have stuff, the space station itself is very big, massive when you compare it to, say, an astronaut that's outside doing a spacewalk. But they're not going to be drifting apart because their masses are different. Their periods are still going to be the same. Given that they were just sitting stable to each other and weren't moving off from each other, they would go in an orbit together for a very long time. Something that's more massive, something that's less massive. Blah, blah, blah. Hopefully that's at least interesting if it's not helping you. Anyways, answer C, is it linear in R? They're playing a game with you and trying to make you think of something else, I'm sure, with that answer. I'd move over that pretty quick because answers D and E would catch my eyes much more. Moving past answer C, I would get to D and E. Proportional to r to the 3 halves, and proportional to r squared. You got a good chance that it's going to be one of those, when it's at least worth looking when you have two answers there hinting that something is proportional to the radius in some measure, for example. Of those two, the one that screams at me is answer D, because it's got the 3 halves. And this, just when I read this the first time, I knew they were hinting at Kepler's third law. And Kepler's third law, I don't want to try and quote it from verbatim because I'm sure I'll screw it up. But it says that the radius, you've got the radius cubed is proportional to the period squared. Okay, and when it talks about the radius in Kepler's third law, it's actually the semi-major axis of the ellipse. The only reason that we just say it's the radius in this problem is because they are saying it's a circle. And so that simplifies to a circle. So if you just manipulate this a little bit, you just get, t is proportional to square root of r cubed, which equals r to the 3 halves, right? And that's what I want, and that's answer D. And so this question is almost, you're not really doing that much math there. It's almost a trivia question. Do you know how to link that up with Kepler's third law and get what you need out of it? I would answer D, knowing that, and then answer E is just kind of a trick. They're hoping you'll get sloppy and just see the r squared and pick that answer in a hurry, but don't. Think it through. And so that's it. I mean, that's it's just a trivia type B question about Kepler's laws of planetary motion. So I would suggest reviewing those, specifically, well, I guess both the second and third ones. Maybe even memorizing both of them, I would say, in some form or manner that you can use, because there are several problems that have something to do with Kepler's laws of planetary motion. So that's it. I'm droning on, so I'll sign off here. That was number 3 off of the 2001 Practice Physics GRE. So as always, thanks for watching.